Now let's take a look at examples showing their application. Example 1. What is the effective resistance of the circuit shown below? Take a look at these circuits. You have 4 resistors. The first 2 are connected in series, and the last 2 are connected in parallel. Now let's resolve this and find our effective resistance. So example 1, let's bring out our diagram again for reference purposes. Have this is a symbol for resistor. So this is what we have. Let's call this R1, R2, R3, and R4. R1 is 5 ohms. This is 10 ohms. This is 2 ohms. And this is 4 ohms. Let's check for correct. Okay, we're good to go. So, the first 2 cases now, like I said, these 2 are connected in series, while these are connected in parallel. So let's resolve the series. For series, R series, let's call it R series. That is resistors in series. R series, or you can call it R series, equals to R1 plus R2, which is equals to 5 plus 10. 5 plus 10 will give us 15 ohms. So our R series now becomes 15 ohms. Similarly, the second point, we have the parallel connection. So we now have R parallel, that is RP, to be equals to, we call that the effective resistance for this is given as 1 all over R parallel, that's RP, equals 1 all over 2 plus 1 all over 4. Now in this case, the LCM will be 4. 4 into 2 is 2, 2 times 1 is 2. Plus 4 divided by 4 will give us 1. 1 times 1 will give us 1. So this is 1 here. We will have 3 all over 4. So R1 over RP now is equals to, this is P, 3 all over 4. Now we're asked to find RP, not 1 over RP. So when you do that, you take the inverse. So we're going to have RP all over 1 is equals to 4 all over 3. So this is our RP. Now, since we've obtained RP, the circuit is going to look like this, because we've resolved the 2 of them. So this is our R series. This is our RP. Our R series is 15 ohms. Our RP is 4 all over 3. Now we're going to get the total effective resistance. Let's call it RT. R means the total effective resistance, which is 15 plus 4 all over 3. This is over 1. Our LCM will be 3. 3 into 1 is 3. 3 times 15 will give us 45. Plus 3 into 3 is 1. 1 times 4 will give us 4. So 45 plus 4 will give us 49 all over 3. Now our R total, which is RT, 49 divided by 3. Divide 49 by 3. Let's see what we have. 49 divided by 3. Having 16.33 ohms. So this is the value of our R total. What we did was that we resolved the resistors in series and that in parallel to get our effective resistance. Let's take a look at another example, example 2. In example 2, they said 3 resistors of magnitude 4 ohms, 5 ohms, and 7 ohms are connected in series and then in parallel. Find the effective resistance in both cases. So our solution, for example 2, we have 4 ohms, we have 5 ohms, and we have 7 ohms. And they say they are connected in series and also in parallel. So for series or series connection, our R1 will be equal to 4 plus 5 plus 7. So our R now is 4 plus 5 will give us 9. 9 plus 7 will give us 16 ohms. That is for series. Then in parallel, 1 all over R equals to 1 all over 4 plus 1 all over 5 plus 1 all over 7. Take the LCM, which is 140. 140 into 4 will give us, let's check, 140 divided by 4 is around 28. Okay, 35. 35 times 1 is 35. Plus 140 divided by 5. Divided by 5 will give us 28 times 1, 28. 140 into 7 will give us 20. 20 times 1 will give us 20. So our 1 over R now equals to 35 plus 28 plus will give us 83 all over 140. Like I said earlier, we're going to find R, not 1 over R. So now take the inverse, which is R over 1, to be equal to 140 all over 83. And divide 140 by 83. 140 divided by 83. We're going to have 1.68 ohms. Now, take a look at this. From our condition, we said that in parallel series, in parallel connection, that the effective resistance is lower than the least resistance or least resistor. So 1.6 is lower than 4, which is the least resistor. That is why this is basically the best method in carrying out wiring in a building. Okay, because the effective resistance offered will be smaller. Okay, so basically we've obtained our resistors in series, that's effective resistors in series, that in parallel. Let's take a look at another example, example 3. Example 3 says, find the sum of the currents I1 and I2 in the figure shown below. Now, how the figure shown? From the figure, we have that the voltage through the circuit is 12 volts. In the first case, for I1, we have two resistors there, 5 ohms and 10 ohms connected in series. In the second case, we just have only one resistor. Now, let's take a look at the solution to this. So, example 3. On the first case, you're going to find I1. Remember that our V is constant, which is 12 volts, and our R1 is 10 ohms. 10 ohms, let's take a look at the question again. R1, okay, you have 10 and 5 ohms connected in series. So in that case, you're going to resolve them to find the effective resistance. So R1 is equals to R for 5 plus R for 10. Our R1 is equals to 5 plus 10, which gives us 15 ohms. So in the first case, we're going to have, from Ohm's law, V is equals to I1 R1. Okay? So to obtain I1, make I1 the subject to the formula. I1 now becomes V all over R1. So our V is 12, R1 is 15. 2 here will give us 6. 2 here will give us, let's use 2 cannot divide 15, so let's use a factor that can go into both of them. So we have 12 all over 5. 15. 3 here will give us 4. 3 here will give us 5. So this becomes 4 all over 5. That is our I1, and it's in amperes. Now let's do for the second case. In the second case, we are looking for I2. Like I said, V is constant, which is 12 volts. And R here, R2 here is just 10 ohms. So similarly, if you use Ohm's law, you have that our V is equals to I2 R2. So if you make your I the subject, our I1 now, or I2 rather, becomes V all over R2. Our V is 12, R2 is 10. So 2 here will give us 6, 2 here will give us 5. So it will become 6 all over 5. We have to find the sum. In finding the sum, this is what we're going to have. Therefore, our sum of current will be equal to 4 over 5 plus 6 all over 5. So when you add, you see that they have the same denominator. So LCM is 5, this becomes 10. So therefore, I2 plus I1 will give us 10 over 5. And 10 over 5, when divided, will give us 2. So this is 10 all over 5, which is equal to 2 amperes. So this is the sum of the two currents, I1 and I2. Now we've taken a look at examples involving resistance, Ohm's law, and current. Now let's take a look at another concept in current electricity, which is the E.M.F. Now E.M.F, I will say, is electromotive force. And we said it is defined as the total work done in driving one column of electricity around the circuit. In some motors, you see that it is defined as total work done in driving one column of charge on the circuit. So it's still the same thing. Also, it is referred to as the potential difference between the terminals of a cell when it is an open circuit, that is, when it is not delivering current to an external resistance. Another term to look at is the internal resistance of a cell, that is the small r. Now, this is the opposition to the flow of current when it is discharging current to a circuit. Okay, that is when the circuit is a closed circuit. Let's take a look at another one, which is the lost voltage. The lost voltage V is defined as the potential difference across the internal resistance R of a cell. In lost voltage, our E.M.F is equal to PD across external resistance plus PD across internal resistance. We have our E to be equal to capital V plus small v. Capital V is the PD across the external resistance, while small v is the PD across the internal resistance. Now, if you apply Ohm's law to equation 1, you're going to have equation 2, where E is equal to IR plus I small r. Factor out the current, have your E to be equal to I into R plus R. Now, this question, or this equation rather, is used basically to find the internal resistance of a cell. Now, let's take a look at the application of this by solving examples. Let's take a look at example 1. A battery of E.M.F 24 volts and internal resistance of 4 ohms is connected to a resistor of 32 ohms. Now, what is the PD of the battery? So in this case, we have E.M.F 24 volts, internal resistance of 4 ohms, and connected to a resistor of 32 ohms. We have to find the PD across the battery. Let's take a look at the solution to this. So in this case, we have our E to be 24 volts, our small r to be 4 ohms, and a capital R to be 32 ohms. We asked to find our V. Now, before you find your V, you are going to obtain your I. You can obtain an I from this formula. Our E is equals to I into R plus small r. So this is 24 into I. This is 32 plus 4. So 24 is equal to I into 32 plus 4 will give us 36. Therefore, our 24 now be equal to 36 I. Divide both sides by 36. 36. This and this will go. For I now will become 24 all over 36. Now we can reduce this to its lowest term. 2 here will give us 12. 2 here will give us 18. 2 here is 6. 2 here is 9. 3 here will give us 2. This is 2. 3 here will give us 3. So our I now will be equal to 2 all over 3 ampere. Now we've obtained our I. So we can use Ohm's law to obtain our potential difference V. So from Ohm's law, our V is equals to IR. Okay, this is I. Our I is 2 all over 3 multiplied by 32, which is a resistor or resistance rather. 2 times 32 will give us, this is 4, 64 all over 3. So our V now become, when you divide 64 by 3, 64 divided by 3, you're going to have 21.3 volts. So this is the potential difference across the battery of the circuit. Now let's take a look at another example under this, example 2. A cell of E.M.F 1.5 volt is connected in series with a resistor of resistance 3 ohms. A high resistant voltmeter connected across the cell registers only 0.9 volts. It has to calculate the internal resistance of the cell. Similarly, we're going to use the same equation to solve this. Example 2. So I'll bring out the parameters. The parameters will have our E to be 1.5 volts. Our R is given to be 3 ohms. Now, given our V in this case to be 0.9 volts. So I asked to find our small r, which is the resistance of the internal circuit, that internal resistance. Similarly, before we get our R, we need to get our current, I. How do we get our current? We can get our current from Ohm's law. So using Ohm's law, our V is equal to IR. Making I the subject, this and this will go. So our I now is equal to V all over R. Our V is given to be 0.9. Our R is 3. So our I now, when you divide 0.9 by 3, you get 0.3 ampere. So that's the value of our current. Now let's obtain our internal resistance, small r. And how do we do that? We can obtain that from the equation where E is equal to I into R plus R. So our 1.5 is equal to 0.3 into 3 plus small r. So 1.5, when you open the bracket, you're going to have this 0.9 plus 0.3 r. So you collect like 10, this becomes 1.5 minus 0.9 equal to 0.3 r. So this will give us 0.6. 1.5 minus 0.9, that's 1.5, 0.9, 0.6 equal to 0.3 r. Divide both sides by 0.3 to obtain your r. This and this will go. So our r now is equal to, when you divide 0.6 by 0.3, you're going to have 2 ohms. So basically, this is the value of the internal resistance of the cell. So we've taken a look at applications by solving examples involving the internal resistance, potential difference, using Ohm's law, and also the equation connecting our external resistance and also internal resistance. Here are some sample questions. Question 1. 3 5-ohm resistors are connected in parallel and have a potential difference of 60 volts. Applied across the combination, you have to find the current. Also, question 2. From the diagram below, to calculate total current in the circuit. If you take a look at the diagram, you can see that the resistors are arranged in parallel. So you're going to find the effective resistance before you can find your current using Ohm's law. Question number 3. Question number 3 says 4 cells, each of E.M.F 1.5 V and internal resistance of 4 ohms are connected in parallel. Now, what is the E.M.F? And also, okay, what is the effective E.M.F? And also the internal resistance of the combination. Question 4. An electric cell has internal resistance of 2 ohms and the current of 0.5 ampere is found to flow when the resistor of 5 ohms is connected across it. Now, what is the electromotive force of the cell? So basically, you've come to the end of this, and here are some references for further studies. Take a look at them. Basically, you have 3 references for further studies. You can take a look at this: Essential Physics, Senior Secondary School Physics, and All-Inclusive Calculation in Physics. Thank you for listening.